Evening. Thank you for being here. My name is Siddarth, and today I'm presenting research on AI-based early detection of Alzheimer's disease using speech and language biomarkers. This work combines machine learning with speech analysis to create a low-cost, accessible screening tool for one of the most pressing healthcare challenges we face today. Alzheimer's disease represents a critical diagnostic challenge in modern healthcare. Here's why. The current diagnostic landscape has three major limitations. First, cost. Traditional diagnostic methods like MRI and PET scans cost thousands of dollars per patient, prohibitively expensive in many healthcare systems and resource-limited regions. Second, invasiveness. These methods require specialized equipment, trained personnel, and infrastructure that many communities simply don't have access to. Third, and perhaps most importantly, accessibility. This creates a massive inequality. Early detection becomes a privilege rather than a right. The solution we're proposing is that we can use speech-based AI detection. Why? Because everyone has speech. It's non-invasive, it requires only a phone or microphone, and it costs essentially nothing to administer at scale. This makes early detection genuinely accessible to underserved populations. Will establish why this matters. The scale of the problem is that over 7 million Americans and over 55 million people worldwide are living with Alzheimer's disease. This isn't a rare condition. It's a global epidemic affecting families and healthcare systems everywhere. Why early detection matters. Research consistently shows that early intervention, when cognitive decline is mild, creates opportunities for timely medical treatment and disease-modifying therapies, family planning and preparation, lifestyle modifications that may slow progression. The scientific foundation is that we know from existing literature that Alzheimer's disease produces measurable changes in how people speak. Patients show alterations in speech patterns, pause behavior, word-finding ability, and fluency. These changes occur before significant cognitive decline is noticeable in standard clinical assessments. The opportunity machine learning is uniquely positioned to detect these subtle speech patterns automatically. The human ear might miss a 50-millisecond difference in pause duration, but algorithms can detect and interpret these nuances reliably. What makes this work what makes this work innovative? Our key finding, one I'll detail later, is that pause duration and timing patterns emerge as the primary distinguishing feature between Alzheimer's patients and cognitively normal individuals. This isn't just about acoustics, it's temporal linguistics encoded in speech. Our research had five specific objectives. First, extract 40 distinct acoustic and linguistic features from spontaneous speech samples. These features span three categories: temporal patterns, acoustic characteristics, and linguistic properties. Second, identify which features actually discriminate between Alzheimer's patients and cognitively normal controls. Not all 40 features contribute equally, some are just noise. Third, develop machine learning models capable of accurate classification. We tested 6 different algorithms to find the optimal approach. Fourth, achieve sufficient sensitivity for clinical screening applications. Sensitivity is critical here. We need to minimize false negatives because missing an Alzheimer's patient has serious consequences. Fifth, ensure explainability. A black box model isn't useful clinically. Clinicians need to understand why the model makes a prediction. Let me walk you through our experimental design, the dataset. We used the Addresso dataset from Dementia Bank, a collaboration between researchers at Boston University and University of Pittsburgh. I should note, accessing this data required institutional partnership. I became a Dementia Bank member and worked through my mentor with researchers Abigail Medvick and Brian McWeeny to obtain access to these valuable resources. Our dataset comprised of 166 participants, 87 diagnosed with Alzheimer's disease, and 79 cognitively normal controls. All participants completed the cookie theft test, a standardized neuropsychological task where participants describe a picture of children stealing cookies from a jar. This task is sensitive to cognitive and linguistic decline and is used clinically worldwide. We used five-fold cross-validation to ensure our results weren't overfit to a particular data split, a critical methodological safeguard. Feature engineering. We extracted 40 features across three dimensions. One, temporal features, which we acquired 13 features from, some of which were pause duration, pause frequency, mean pause length, speech rate, total speaking time, and essentially the rhythm of speech. Our second was acoustic features, which we extracted 13 features from, some of which were MFCC coefficients, spectral centroid, spectral roll-off, zero crossing rate, and basically the sound quality of speech. Our third was linguistic features, which we extracted 14 features from, some of which were semantic coherence, semantic similarity, verbal fluency, lexical diversity, and essentially the language content of speech. Important methodological note is that the addressable dataset came from pre-extracted acoustic features and segmentation. We applied no additional preprocessing. The structure was already provided, which actually reflects the real-world scenario where standardized processing pipelines ensure consistency. Moving to our results, let's start with the most informative features. Figure 1 shows a box plot comparing 6 features between Alzheimer's patients, shown in red, and cognitively normal controls, shown in teal. What we observe is that the most striking finding, mean pause length, shows a clear, distinct separation between groups. Alzheimer's patients exhibit significantly longer pauses. This difference is statistically significant at is lesser than 0.001, well beyond the threshold for clinical relevance. Spectral features is the centroid and roll-off show more overlap, but it will display trends distinguishing the groups. Interestingly, total speech duration is similar between groups, but the distribution of pauses within that duration differs dramatically. An Alzheimer's patient might speak for 60 seconds, but 20 of those seconds were spent pausing, whereas a control might only pause for 5 seconds. The key insight here is that it tells us that temporal features, how speech unfolds in time, are stronger discriminators than raw acoustic features alone. This makes clinical sense. Cognitive decline affects the executive function and word retrieval, which manifests as increased hesitation and pauses. Next, we examined how these 40 features relate to each other. Figure 2 is a correlation heat map. Red indicates high correlation, blue indicates low correlation, and white is neutral. What this reveals is that temporal features show very high correlations with each other, 0.7 to 0.95. This makes sense. Pause duration, pause frequency, and speech rate are inherently related. This high redund- this high redundancy means we can potentially reduce dimensionality without losing information. Importantly, acoustic and temporal features show weak correlations, which are around 0.5. This suggests that they capture complementary information. They're measuring different aspects of each decline. Figure 3 is a 2D PCA projection showing how well these features separate the two groups where dimensionality is reduced. PCA, Principal Component Analysis, achieved 47% of total variance using just two components. PC1 captures 25.6% and PC2 captures 21.4%. This is significant because it means that we can deploy a reduced dimensionality model without substantial performance loss. The scatter plot shows moderate group separation, some overlap, but clear clustering by group. This suggests that features have predictive power, though no single linear combination is perfectly separable. The implication of this is that these features provide complementary, non-redundant information. This complements our deployment goals. We can use dimensionality reduction for efficiency without sacrificing discriminative power. Now, the critical question. Which machine learning model performs the best? We trained 6 algorithms: logistic regression, random forest, gradient boosting, and SVM, both linear and RBF kernels, and finally XGBoost. Here are the test results. XGBoost emerged as the clear winner, with an accuracy of 70.59%, an F-score of zero point 0.7, an ROC-AUC of 0.691, and sensitivity, which is the most clinically relevant, is 83.3%. For comparison, Random Forest scored 64.71% accuracy. Gradient boosting, gradient boosting performed 58.82%. SVM linear performed 52.94%, and RBF performed similar. And logistic regression performed 58.82%. Why does XGBoost win? XGBoost is an ensemble-based method that combines multiple weak learners sequentially, each learning from the mistakes of previous iterations. This architecture allows it to capture non-linear relationships between pause patterns and Alzheimer's disease. Relationships that simpler models like SVM or logistic regression cannot detect. And why is 83.3% sensitivity particularly important? In clinical screening, sensitivity, the true positive rate, is more critical than accuracy. Missing an Alzheimer's patient false negative has serious consequences. A high sensitivity means our model catches most actual cases, even if it occasionally produces false alarms. Figure 5 shows feature importance using prediction gain. Notice that mean pause length ranks first. It contributes more to model predictions than any other feature. This validates our earlier observation from the box plots. Acoustic feature Acoustic features provide important but secondary contributions. Why are tree-based models superior here? Tree-based models excel at capturing the nonlinear threshold effects in speech patterns. For example, there isn't a simple linear relationship where more pauses always mean more Alzheimer's. The relationship is more complex, involving interactions between features. Trees naturally capture this complexity. Let's examine the statistical significance and population heterogeneity revealed by our data. Figure 4 shows Violin plots. These combine distributions with individual data points, giving us insight into shape and spread. What we observe is that pause metrics show highly significant differences, where p is lesser than 0.001 using Mann-Whitney U-tests. This is non-parametric statistical testing, appropriate here because pause data isn't normally distributed. The Alzheimer's group shows bimodal distributions, meaning that there are distinct subpopulations where 80 patients um, within 80 patients. Notice the wider spread in the 80 group, red, versus the tight, homogeneous CN distribution, which is teal. The CN group shows classical normal distributions, tighter and more predictable. Spectral features show subtle but significant differences where p is lesser than 0.05. Statistical valid but with smaller effect sizes. Clinical implication is that the heterogeneity in AD the presentations suggest subtype-specific models might improve detection further. Some Alzheimer's patients show dramatic pause changes. Others show more linguistic symptoms. Future work could segment AD, classic normal distributions, which are tighter and more predictable. Spectral features show subtle but significant differences where p is lesser than 0.05, statistically valid but with smaller effect sizes. And I was restating the clinical implication. The heterogeneity in AD presentations suggests subtype-specific models which might improve detection further. Some Alzheimer's patients show dramatic pause changes, while others show more linguistic symptoms. Future work could segment AD patients by phenotype and train specialized models. Let me synthesize what we've learned. First, speech-based machine learning achieves 70.59% accuracy, which with 83.3% sensitivity for Alzheimer's detection. On a dataset of over 100 patients, we correctly identified approximately 83 cases, which is a meaningful clinical performance. Second, temporal features. Pause duration, speech rate, hesitation patterns are the primary discriminators, not acoustic features alone. This challenge previous assumptions this challenges previous assumptions in the field that acoustic properties dominate. Third, XGBoost with explainable features importance enables real clinical deployment. We can tell clinicians exactly which features drove each prediction, supporting human decision-making rather than replacing it. Fourth, this tool democratizes early screening in low-resource and telemedicine settings. A patient in rural Africa with a smartphone can potentially access early detection capabilities that rival hospital-based imaging. Fifth, future work should validate these findings on diverse language populations. Our dataset was primarily English speakers. Integration with other clinical biomarkers through blood tests, imaging when available, could create hybrid models with even higher accuracy. The bigger picture is that this research exemplifies how AI isn't about replacing doctors, it's about extending their reach. Early Alzheimer's detection remains rare in many populations, simply due to these access barriers. Speech-based screening removes that barrier.